So where we left off yesterday was discussing different associative containers. We're starting with the ordered containers. We talked about the set and multi-set containers yesterday, and today we're going to start talking about map and multi-map. For my money, map is arguably the coolest container in STL. It's really fun, and we're going to have a good time talking about several different examples that illustrate the features of map. So a map is essentially what's sometimes called an associative array. It's a way of being able to associate a value with a unique key. So maybe an example would be having a student ID number and then associating that ID number with student records or student classes or something like that. The value type of a map is implemented as a pair with const key and data. So much like we discussed with set and multi-set yesterday, the idea behind map is that the iterators are going to be const. So at least the parts that are iterating over the keys are const, because we don't want to accidentally or maliciously change those values, because that would upset the internal data structure for the map. Recall that a map is implemented as a red-black tree, an ordered balanced binary tree for the ordered associative containers. And we'll talk more about those here shortly. Okay, so let's now switch over to our IDE, and we'll start to look at some code. So first, in the comments section here in this code, it talks a little bit more about what an associative container is for map and how it has to have unique keys. It gives the signature for a map, which is arguably the most complicated signature we've seen so far for an STL container. So it's parameterized by key, which could be something like a string or an int or whatever. A value, which could be the same as key or could be different. There's no reason they have to be the same. The comparison operation, which is used to do the ordering in the red-black tree. And then finally, an allocator that will allocate this pair of const key and value. So that's what has to be provided to a map. Now, as you can see, the comparison functor and the allocator are both defaulted, so you really just have to provide the key value pair. So the characteristics of a map that are important to remember: inserting a new element into a map doesn't invalidate iterators that point to existing elements. If you erase an element from a map, that also doesn't invalidate any iterators, unless, of course, you erase the item that you're iterating over, in which case, yes, of course, it's going to be invalidated. So if you want to use a map, you have to provide the key and key type and the data type, and you can also choose to provide the comparison functor if you want, but if you don't, it'll just default to less. Okay, so here's the fun example, and this is interesting. What this example does is it's going to have a list of words, and it's a famous phrase. I'm not even sure where this phrase is from, but it says, "Now is the time for all good people to come to the aid of their party." And we store this in a vector of strings. So you can see that word list is a vector of strings. And then we're going to go ahead and type def a map here to be a map of string, which string is the key, to int, where int is going to be a count of the number of times the word appears in the map, or more specifically, the word appears in the word list we're going to use to initialize the map. And then we go ahead and take that type def and we make ourselves an instance called word map. So word map, all caps, is the type, and word map is the variable. And now what we're going to do is we're going to use this really cool little range-based for loop that's going to iterate through every element in word list, and it's going to go ahead and index into the word map using the subscript operator. And it's going to basically say word map sub word. So that's why this is sometimes called an associative array, because it looks like an array. And then it's going to go plus plus whatever it finds there. And of course, what it's going to find there will be the value. So what we're doing is we're indexing into word map using word as the key, and then we're incrementing the value, which is a count of the number of times that word appears in whatever input we're iterating over. So a couple things to note here. Note how clean and concise this is. Notice how we're using an auto const ref for word, which means that we're pledging not to change it. And it also means that it's deducing the type. It's of course an iterator type here. and we're using ref so that we don't end up making an unnecessary copy. So that's what that code looks like. Now, just for kicks, there's other ways to write this as well. And I'm just going to show them to you. My preference, of course, is for the version that I show here, which is the range-based for loop. This came a little later in C++, and I think it was C++ 2011 is when it was introduced. Before that point, you had other ways of doing things, and that is kind of the classic way of using iterators, but I think they're more verbose than we would like. So, but here they are just for completeness. So one approach here is to use an explicit iterator. So you say word map : iterator, word iter is set equal to wordlist.begin. And of course, we probably should be good and say cbegin because it's really a const. And then we keep iterating until we reach the end by cend. And for each element, we go ahead and dereference the word iterator and go ahead and increment or go ahead and subscript that or index that into the word map and increment the count. And then we plus the word iterator. So I think you'll agree with me that even though this code is kind of more classic iterator pattern and classic STL, it's also more verbose. One way to get rid of some of the verbosity is to get rid of using word map : iterator and just say auto const ref word iterator. So that uses the type deduction features that were added to C++ 11. And that's a little bit more concise, but let's be honest, the range-based for loop is by far the most concise way of doing things, and it's just so clean and sleek and elegant. So I would recommend sticking with that for the most part in modern C++. Of course, if you end up working on a legacy project that doesn't have C++ 11 compiler features, then you may have to be able to know how to use the older, more classic version. But I like the newer version a lot better. So once we've got ourselves a word map that's been initialized to keep count of the number of times each word appears in the word list, now let's go ahead and print this out. And you can see what we're going to do is, once again, we're going to go back to our range-based for loop, and we're going to iterate through the word map again, and or we're going to iterate through the word map before we iterated through the word list. Now we're going to iterate through the word map, and every time along the way, we're going to have an iterator I, which is going to be a value type, and the value type for a map is going to be a pair, and the pair is going to have the first field in the pair, the first data member in the pair be this const, which will be a const string, which has the name first, and then it has a second field or second data member, which is going to be called second, which in this case is an int. So you can see here what we're going to print out is a count of the number of times the word appeared followed by the word itself. And we do that just because it's easier to format it that way. All right, so I'm going to go ahead and run the code just so you can see what it does. I think it's worth looking at. So you can see that it goes ahead and prints out the contents of the map with the number of times each word appeared first. And also you'll notice that it comes out in ascending sorted order, because that's what a word map does. It stores it in sorted order. So you can say aid, all, come, for, good, etc. All those have a count of 1, and then the and to have a count of 2. So they get printed with 2 instead of 1 in the beginning. But notice how it's sorted. And then the last thing we do is we're going to go ahead and show a couple of different ways to count the total number of words. And there's a total of 16 words here, as you can see. So we're going to do this a couple different ways. The first way we're going to do it is going to use a functor. And a functor is essentially a struct or class that defines operator function call. So you can see here's operator function call. And in this case, we're going to pass it the value type of the map with a const ref. And it's going to go ahead and just increment a local or a private data member, which keeps track of the count. So you can see that the way this works is the constructor for this struct called totalit is passed I, which will of course be 0 originally. And then it keeps I here, keeps track of I. And then whenever its operator function call is invoked, it goes ahead and takes the second field in the pair, which of course is the count of the number of words, that the number of times that word appeared, and it goes ahead and it plus equals I. So that's what totalit is going to do. So let's see how we could use totalit, how we could use this functor. So down here we give ourselves an int or an auto 0, And then we go ahead and use the for each algorithm. We'll look at for each in a second. What for each is going to do is it's going to walk from the beginning of the map to the end of the map. And every time through, it's going to call an instance of the totalit struct. And we'll talk about how that gets passed to the for each algorithm in a second. But you can see that totalit, when it's called, it's passed total, which starts at 0. And then you can also see that for each is going to return an instance of totalit. And it turns out that the instance of totalit that it returns is the one it's been using internally to keep that running count of the number of times that the count of the number of words that we have encountered in our program. And when we're all done, we go ahead and say it for the totalit object dot I underscore, and that's the total. And then we print out the total number of words is total. Okay, so let's take a look at a couple things here. First, let's take a look at for each. Hopefully this will work. So here's the for each algorithm. You can see it starts at the beginning of the range, goes to the end, and every time through it calls the function that's passed in as the third parameter to for each. Now, you can see it's denoted here as function, and you can see up here it's just a class, or could be type name also. And so at first glance, it looks like it's a function. And it could be a function, but in this case, it's actually a function object or a functor. And you can see that the functor, I like the word functor, it's cool. The functor is an anonymous instance of the totalit struct that's been initialized initially with 0 for total. So totalit creates an anonymous object. That anonymous object is passed in as the third parameter to for each. And then down here where the function call is being invoked, what that's really doing under the hood is that's actually calling this operator function call on the totalit struct. And so what we're doing is we're passing in a functor or function object that has the function call operation defined. And that's pretty cool. And you can see in this particular case, this functor can actually store state. It stores total, which is set in its constructor. And if you go back and look at for each, you'll notice that this function is called every time, but in fact, it's actually calling a function object, and that function object can store state. And when we're done, for each returns that function object by value. So you can see it's coming back here as a function or as a function object. And we take the result of that and we store it in this local variable called it, and then we can go ahead and extract the count from it. So that illustrates how you can basically pass an object in to the for each algorithm. It can be used locally throughout the duration of the algorithm as it does its thing, and it can update its internal state. And when it's done, it returns that function object by value, which we can then store and then do something with. So that's a pretty cool example of the capabilities of functors and of for each. Well, let's take a look at another way to do this. So this is one way to do things, but the problem is we end up having to define this extra struct. And even though it's not the end of the world, it's just a little bit extra syntax that we might like to avoid. So an alternative way to do this is to use a C++ Lambda function. And a Lambda function is just a little snippet of code that we can put into places that functors are expected. And basically, the C++ compiler doesn't require us to make a named struct. It doesn't require us to say operator function call. It allows us to leave a lot of syntax off. And this is a good example of kind of generic programming meets functional programming, because the concept of Lambda expressions is very common in functional languages. Java, modern versions of Java also support something very similar to this. The syntax is slightly different, but the concepts are the same. So here you can see we have the for each call this time from beginning to end of the word map range, except rather than making an instance of some functor that we have to define here, instead what we're going to do is we're just going to define a Lambda function. And what you can think about the Lambda function as being is this part is the key part here. This is the parameter that's being passed. And that corresponds to what's the parameter to the operator function call method that's defined up here in totalit. So it's like we just kind of pull that out, leave away all the other syntax, leave away the name. So it's basically an anonymous piece of code. And what it's going to do is it's going to say total plus equal to p second, where p is the parameter that's passed to this lambda. And that parameter, of course, corresponds to a given element that we're iterating through in our range from beginning to end. Now, there's still one more piece of the puzzle that we have to explain here. You'll notice that total is actually a local field or a local variable that's defined in this main function. And the semantics of C++ is that you can't access variables from an outer scope inside a Lambda function unless you explicitly provide access to it. So there's a couple different ways to do that. One way to do that is to do what I do here, where I say ampersand total. And what that says is pass in total by reference. So it means that it can be updated. So if we do total plus equal, that will actually reflect a change to the value of the local variable. If we don't do this, for example, if we just completely leave this off altogether, then you'll see it's going to complain and say, what the heck is total? I don't know what total is. I can't do anything here. Likewise, if we were to say total like this, then it would pass it in by value, and we basically be const, and so we couldn't modify it. So we have to say address of, so it's kind of like saying by reference, if you will. And so those are some ways that you can pass stuff in. Now, another thing you can do here is you can just put the address of operator, or the ampersand operator, here, and then that says anything in the local scope can be accessed within this Lambda function. Now, that's probably a little bit too permissive, and so I like to be explicit here. I just like to say, these are the things I want passed into my Lambda function. Now, an obvious question to ask at this point is, when should you use a Lambda function like this versus using a functor, an explicit functor like we show up above? And the basic rule of thumb is, if you plan to reuse the same Lambda function multiple places, then you're better naming it and making it a functor. And we'll see lots and lots of examples of this. For example, STL defines a whole pile of functors like greater and less and plus and minus, and so on and so forth. And those are things that get reused all over the place. So rather than having to rewrite that code over and over again, let's just use the pre-existing functor, or one that we might build. You'll see a lot of examples in my code where I use is odd or is even as a functor. So rather than having to remember how to do the computation for is odd and is even, you can just reuse the functor. So if you're going to reuse the computation, make it a named entity like a struct or a class. If you're not going to reuse it, then maybe you can just go ahead and plop the Lambda function code in there. So those are some good rules of thumb to keep in mind when using these features. A couple other things to note. This is a stateful functor, and in production code, I probably wouldn't have been so cavalier to make it a struct and expose its inner workings. I probably would have been better off doing something like this, where I could have said class total it, and then said something like public, and I'll make this guy down here be private, so it's hidden. And then maybe what I could have done was to have said something along the lines of, I don't know, int count return I. And down here, then, of course, that would become it.count. So that's arguably a little bit more expressive, and it states its case a little bit more cleanly. Let's make this a const method. So the downside there, of course, is now my functors get even bigger. And so you have to kind of pick your poison, which is the best thing to do. Are you trying to make something that's very abstract and be reusable and documentable, or are you just trying to get the job done? And clearly, for bigger systems with more users and more at stake, you would go with something that was better thought about and better documented and better abstracted and so on and so forth. Okay, so that was the first example that I want to show you today. Let's now go and look at another example. And this will be part of the, this will still be part of the map family of discussions. We haven't moved on yet. So this particular example is just going to show off a few other features of maps And we'll also show some other things you can do. We'll define another functor. This particular functor is a stateless functor. And when you have a stateless functor, it probably makes more sense to make your stateless functor be a struct, because we're really just using this to provide an enclosing data structure for operator function call. So making it a class and putting public and all that stuff in is probably overkill. For simple stateless functors like this one, probably best to make it a struct. And in this particular case, you can see what we're going to do is we're going to define operator function call to print out the contents of the map. So that's what we're going to do. Okay, so and then down here, we're going to go ahead and create ourselves a pair where we have a string to int mapping. We're going to say we're in seventh heaven, little phrase. And then we're going to go ahead and print the contents of this. And down here, we're going to go ahead and make ourselves a unique pointer, which is going to point to a new pair. And in this case, it's going to be a pair of string to int mapping, which is going to be the whole 9 yards. We're just going with little cliches, or aphorisms, as I think they're called. So in that case, we've got a pointer. We've allocated it as a pointer. It's a pointer to a pair. And that, of course, is being accessed as a unique pointer, which is kind of a smart pointer. And we can go ahead and access its first and second fields by using the arrow operation on our unique pointer object. And remember that unique pointers will automatically be cleaned up when they go out of scope, very much like your scoped array that you've been working on for the past couple of assignments. Then down here for kicks, we're going to define a German to, rather an English to German dictionary using a map. Maps are very good for things like dictionaries because it's basically key value bindings. And this will map string to string. So we have shoe being schön, and we have head being Kopf, like Dummkopf. And then down here, we're going to make ourselves a value type of a map of string to string, where we're going to define yes to be ja. And then we go ahead and we insert that instance into the map. So these are showing a couple of different ways to initialize entries in a map. One way is to use operator subscript, where we can say, here's the key, head, and here's the value, Kopf. Or we can go ahead and make ourselves a value type instance, which is used with the wonderful features of STL. And that will go ahead and then allow us to insert that in there. And let's see, I don't know if we can do auto for this. Let's see if we can do auto. Yeah, it gets confused in that case. You can tell it wasn't going to like it because it didn't give us the option to do that. So you have to explicitly say string or map string, colon, value type in order to indicate what you're trying to do here. All right, so let's go ahead now and do some operations with our little English to German dictionary. First thing we're going to do is use the venerable for each algorithm to iterate from beginning to end through the dictionary. And we're going to go ahead and print out each element. And you can see that this print call creates an anonymous instance of this stateless functor called print, whose operator function call simply prints the first and the second element that comes in it as a map string, colon, value type. So that's the element that's stored in the map, and we're going to have that passed to us as a const ref. So that's what you get each time when you iterate over a map from beginning to end. You get a value type, which is this string to string mapping in this particular case. And we have that passed as const ref to avoid copying overhead. Then what we do is we go ahead and we find the element in the map for yes. And we store this as an iterator. And of course, if we want to make this an explicit type, you could see that we would say map string, colon, iterator. But my goodness, that's verbose. So let's just say auto, which is a much more clean way to do it. And if it turns out that we found a match for yes, which of course we should, but we need to check anyway for completeness, then we're going to go ahead and erase that entry from the map. So you can see that if you have an iterator to an entry in the map, you can go ahead and erase the entry. You can erase it other ways as well, but a common way to do it is to get an iterator and then you can erase it. And that will remove it from the map. And to prove that it removed it from the map, we're going to use our good friend for each again to go through the map from beginning to end. And this time, just to be different, we're going to use a Lambda function instead of using the mechanism we did before, which was to have an anonymous instance of the print functor. So if you think about it again, it's kind of like we went up here and just copied this part of the code from the functor and just plopped it down here, and we just put this open close square brackets as syntactic sugar to say, hey, this is going to be a functor. And that's very similar to what you see with Java. Java has slightly different syntax for that. It's open close paren arrow, but it's basically the same idea. So we're just saying, here's an anonymous piece of code that needs to match whatever the iterator is iterating over at the time. All right, so armed with that knowledge, let's go ahead and run the program and see what happens. And you can see here that what we get is we get, heaven equals 7 and the whole 9 yards as the first things we print out. And then we're going to get a map that has head equals conf, shoe equals shoe, and yes equals ya. We remove yes and ya, and then we just get the other entries after we remove the one entry. All right, so that's map. And like I said, I absolutely love map. Map is the coolest thing ever. And we're going to see multi-map in a second, but it's just a basic little extension of map to allow non-unique keys.